Assalamu alaikum, my dear students. Let's move on to the next lecture. And you must possess the hard copy or soft copy of my notes and the relevant book before you. Okay, now in this lecture we would introduce a very strong technique to solve any differential equation, any homogeneous differential equation, and you can consult pages 452 and 453 with reference to the last part of my previous lecture, and you should also go through this example 8.4.1 at page 453 to see the role of the singular points at infinity. And you must also try and solve the exercises 8.4.1, 8.4.2 from the book by Arfkan 3rd edition, and you must also look carefully on table 8.3 at page 454 so that you can recognize the regular singularities and the irregular singularities of these 8 equations. We will see later on that when we separate the Helmholtz equation, as we did for spherical polar coordinates, and we do it for the rectangular coordinates and cylindrical coordinates, this equation furnishes, this separation of variable furnishes these 8 equations which you can say represent the entire physics. So I would ask you to recognize these differential equations and their names. This is the hypergeometric equation, this is the Legendre differential equation, this is the Chebyshev differential equation, confluent hypergeometric, Bessel's differential equation, which I told you is the most common equation in physical problems. We will solve this equation using the Frobenius series method. And then we have Laguerre differential equation and the simple harmonic oscillator and the Hermite equation. So most important of these are the Bessel's differential equation, the Legendre differential equation, which is the next common differential equation, and we have the Hermite differential equation and simple harmonic equation. So you must go through this table and then solve the exercises 8.4.1 and 8.4.2 as a home assignment. So mind you, you will have various quizzes and the assignments and your midterm and final term examination, and the problems or exercises I mentioned during my lecture. You must solve these exercises and do the solution. Okay, so let's now come to the series solution, the Frobenius method, which has been given here. You can either go through the book pages or you can consult my notes for the detailed steps. So here are my notes that we show you the detailed steps here for the series method. Okay, so these are the singular points, which we discussed in the previous lectures, and now is the series solution method. So if you have the book pages and my notes side by side, you will easily follow. Okay, so this equation as written here, 5.4, is the most general form of the differential equation of order 2. Okay, so we will solve this differential, we will apply this method, we will introduce this method by solving this example 5.2. So we will solve this famous equation which covers most of the mechanics and the classical mechanics of physics, and this is the equation d2y over dx square plus omega square y equal to 0. This, as you know, represent the differential equation of harmonic oscillator. You know that most of the physical bodies, they do this harmonic oscillation, and this equation is seen there, and we have to solve this. So let us now discuss, and you must also know that we already know the solution of this differential equation, as this is a differential equation of order 2, so it must have two solutions. The first solution is y is equal to sine omega x, and the second solution is cos omega x. This we have obtained from other methods, but let's see whether our technique series, Frobenius series method, furnishes the same solution or not. Okay, so the first step towards the series method is to assume or to take the Frobenius series of the solution. So we will say that our solution y is in terms of an infinite series as written by equation 5.7. So this series is x to the power k bracket a naught plus a1x plus a2x square, that is the coefficients along with the ascending powers of x, but this power is also there, and you can write this series in this form, and you know that this series is an infinite series. So we will assume our solution in this form. That's why this method is called the series method. Okay, here we will also take that the first coefficient a naught corresponding to lambda is equal to 0 must not be 0, because if this is 0, then the entire other coefficients will also become 0. So the first coefficient a naught must not be equal to 0. The other coefficients out of these infinite number of coefficients, some of these coefficients may be 0, but the very first coefficient must not be 0. Okay, so if you assumed your solution in this form, now let's take the first derivative, which comes out to be this, and we take the second derivative, which comes out to be this, as you can see easily, and then we substitute the values of y, y dash and y double dash into our differential equation. So that is the second step. First step is to assume the solution in the series form, and then we substitute the values of y, y dash and y double dash in the given differential equation. So as soon as we do this and do a little bit simplification, we get this equation. Equation 5.8 written here. Okay, so this each term contains an infinite number of terms with corresponding to lambda is equal to 0 to infinity, and lambda this second term also. So here if we write only the terms with minimum power of x, okay, so look for the minimum power of x from each term, So as you see from here, in this term, when you substitute lambda is equal to 0, the minimum power of x comes out to be x to the power k minus 2. Okay, now the coefficient of the minimum power of x power k minus 2, from this is a naught into, so we put lambda is equal to 0 into k minus 1. So that is the coefficient of the minimum power of x from this term. Similarly, now we will find the coefficient of the minimum power, that is x to the power k minus 2, from the second term. And if we look carefully on the second term, we see that with lambda is equal to 0, the power of x is x to the power k, which is not the minimum power of the first term. So it means the coefficient of the x to the power k minus 2 is not present here, so we will write 0 for this. So this is the then total coefficient of the minimum power of x of the left hand side of this equation, and the right hand side is 0, so we must put this equal to 0, right? So now because a naught is not to be 0, so it means that k into k minus 1 must be 0. So this equation, which is obtained by comparing the minimum power of x on both sides of our differential equation, this equation is known as the indicial equation. So this equation coming from the coefficients of the lowest power of x, we will call it the indicial equation. So that was the second step. In the third step, we will find what is known as the recurrence relation. So mind you that when we can only write our solution if all these coefficients a0, a1, a2, a3 are determined. So we cannot find all these coefficients individually. However, if we can get an expression which correlates a coefficient a lambda with the coefficient a lambda plus 1, so that equation will be very useful in determining the coefficients of our series solution. So that will be the recurrence relation, and the recurrence relation is obtained by comparing the general coefficient of the general power of x. Okay, the general power of x, let's take it x to the power equal to x to the power k plus j. So this is the general power of x. So we will try to find out the coefficient of this power from each term. So if we look at this term and you want to get x to the power k plus j, you will have to write lambda is equal to j plus 2. So the relevant coefficient is then aj plus 2 into k plus j plus 2 into k plus j plus 1, as you can see from here by putting lambda is equal to j plus 2. Okay, and the coefficient of the power x to the power k plus j from the second term will be obtained by putting lambda is equal to j, so we get this term. Okay, so this is the right hand side of the coefficients of the general power of x from the right hand side, and the left hand side being 0, so it must be put equal to 0. So as soon as we do this, we get this expression, and from this expression we get equation 5.10, and that equation is very useful because it correlates a coefficient aj plus 2 to a previous coefficients. So supposing you know a naught corresponding to j is equal to 0, it means you can find a2 by putting j is equal to 0 in this expression. And if you find A2, you can move on to A4, and by recurring this equation you can find all the even coefficients. So that's why we call it the recurrence relation, which is useful. And we may now note here that if we start with A naught, the recurrence relation will give us A naught, A2, A4, A6, etc. So it means the even based coefficients are known, however the odd based coefficients are missing. So don't worry about these missing coefficients, because the even coefficients which make up half of this infinite series, the half of infinite series is also infinite series. So as long as you get even coefficients or odd coefficients or both, you will be able to write your solution. Okay, so now look at the indicial equation. This indicial equation has two roots, has two values of k. One is k is equal to 0, the other is k is equal to 1. Now these two roots of the indicial equation will give us the corresponding two solutions of the differential equation. Okay, so when we put k is equal to k is equal to 1 in our recurrence relation, we get this equation. Okay, from this equation, starting from A naught, we find A2 by putting j is equal to 0, and this is equal to this as written here, and then by putting the value of this A2 into this equation again, you will find A4 and so on. So you are able to find A2, A4, A6, etc. And from here, the general coefficient, that is A base 2n, is equal to minus 1 power n omega power 2n over 2n factorial, as you can see from here. So your first solution will become by putting these coefficients into the assumed infinite series, Frobenius series, and that solution is written here. So this solution is obtained by putting the first root k is equal to 0 of the indicial equation. Okay, so this is the first solution of the concerned differential equation, and you must recognize that this term in bracket is in fact the infinite series of the function cos omega x. So we see that our first solution comes out to be a naught cos omega x. So, and this is exactly the same solution as we pointed out earlier, which is the solution of the harmonic oscillator. Okay, so you repeat this process for the second root of the indicial equation with k is equal to 1, and follow all these steps to reach to the second solution of your differential equation corresponding to k is equal to 1, and we recognize that this second solution is in terms of sine omega x. So this is a naught over omega sine omega x. Okay, so that was the series method. Very simple, containing few steps. First step is to assume the series. Second step, to substitute the values of y, y dash, y double dash. Third step, to find the indicial equation and the roots of the indicial equation. Fourth step is to find the recurrence relation, and then use these recurrence relations to find the various coefficients. Substitute these various coefficients into your assumed infinite series, and you come across with the solution of the differential equation. Okay, let's do the same process for the most famous equation, as I told you, which is x square y double dash plus xy plus x square minus n square y. This is the Bessel's differential equation, which you can see in 60 or 70% of the problems regarding physics. So we now apply the series method. This is the series. The first derivative of this series the second derivative of this series and substitute the values of y dash and y double dash. So you get this equation as written here, which is the result of putting the values of the of y dash and y double dash, and you end up with this equation. Okay, now by setting lambda is equal to 0, the coefficient of x to the power k is the lowest power of x appearing on the right hand side, and when we compare the coefficients of the minimum power of x, this is the coefficient of the minimum power of x on the left hand side, and the right hand side is 0. So from here we get the equation a naught into k square minus n square is equal to 0, and because a naught is not 0, so the initial equation is then k square minus n square is equal to 0. So you have two roots of k, which is plus n and minus n, and these two roots will furnish you the two solutions of the differential equation. Okay, I have done the rest of the I have obtained the recurrence relation by comparing the general power of x, which is x to the power k plus j. So please follow these steps carefully to find the recurrence relation. This is the recurrence relation, aj plus 2 minus aj 1 over j plus 2 2n plus j plus 2. We have already substituted the first root, that is k is equal to plus n. So we have substituted k is equal to plus n and got this recurrence relation. And from this recurrence relation, starting from a naught, we have proceeded to find the coefficient a2, a4, a6, and these, and so on. We can find the other coefficients and the general coefficients, because these are the even, so we will write 2p, a2p is equal to this. So this is the general coefficient with k is equal to plus n. Okay, so our first solution will be obtained by putting these even coefficients and taking the odd coefficients equal to 0, because they are not present here, and you can find your series solution written this with k is equal to n, and we have substituted lambda is equal to 2j. So this is the series solution, the first series solution of the Bessel's differential equation, and we have rearranged this series in this form. So this is the standard form of the first series solution of the Bessel's differential equation. Okay, so let me repeat this. The first series solution of the Bessel's differential equation corresponding to k is equal to n is yx a naught 2 power n summation j is equal to 0 to infinity minus 1 power j n factorial over j factorial n plus j factorial x over 2 n plus 2j. So you will have to remember this series as the solution, the first solution of the Frobenius series solution of the Bessel's differential equation. Okay, what about the second? We have to repeat these processes, but luckily, as you know, that the second root is k is equal to minus n. The first root was k is equal to plus n, and the second root is k is equal to minus n. So you simply put n is equal to minus n, and you reach to the second solution, y x is equal to with n is equal to minus n. So this solution with n is equal to plus n this solution has been symboled as JNX, and the second solution will be symboled as J minus NX. This JNX is called the Bessel's function. Okay, so remember this name, recognize this name. This is the Bessel's function of first order, which is in fact the solution of the Bessel's differential equation as written here. And similarly we can find J minus Nx. Okay, so that was simple. We have applied the Frobenius series method to solve this most important differential equation of physics. Bessel's differential equation we have already done for the harmonic oscillator, so we have covered almost the mechanics and the other main fields of physics in solving these two equations. Okay, so that's all for this lecture, and we will continue for the next lecture, and you must try these exercises written here. Okay, I will assign these exercises in the, let me see if I can do it now. This is the series method as given here. You can go through these pages of the text book, and along with my notes you will be able to understand each step. Okay, after doing this, let me go to the book. Okay, so this is the book in fact. Okay, I will assign you the homework in the form of few exercises in the next lecture. Right, thank you very much.